Hello everyone, I'm back with another physics video, and this unit is on energy, and I'm going to go over homework number 1, 2, and 3. And number 1 says that identical twins Pat and Chris are painting a house. Pat is standing on the scaffolding 5 meters above the ground. Chris is standing on the scaffolding 5 meters above Pat. Who has more potential energy? The answer is Chris because he is higher. Since potential energy is mgh, the masses are the same, the gravity is still the same, but the height changes because Chris is 5 meters above Pat, and since the height for Chris is larger than Pat, thus Chris has more potential energy. And number 2 says Jared and Clay are climbing the stairs. If Jared gets tired and stops halfway to the 4th floor, Clay makes it to the 4th floor without a problem. If Jared is twice as heavy as Clay, who has more potential energy? This is kind of a trick question because the answer actually is that they both have the same potential energy. Jared gets tired and stops halfway, so that means the height is half of what Clay is. G is obviously still the same, but the mass of Jared is twice as heavy, so 2 times 1/2 is 1. So basically, the potential energy is the same for both of them. Number 3 says, a person weighing 630 newtons climbs up a ladder to a height of 5 meters. How much work does the person do? Determine the increase in potential energy of the person from the ground to this height. Where does the energy come from to cause the increase in potential energy? 630 newtons times 5 meters equals 3,150 joules. That is the amount of work that the person does, as you remember from our last unit. And the increase in potential energy comes from the height. Obviously, from the equation P equals mgh, since if you are going up, your mass obviously doesn't change, the gravity is still the same, but as you go up, the height increases, and therefore the potential energy increases. Number 4 says to calculate the kinetic energy of a 750 kilogram car moving at 13.9 meters per second. What is the kinetic energy of the car if the speed is doubled, and how much work must be done to double the speed? And first off, we need to have our equation here, our formula here, and kinetic energy equals 1/2 mv squared, and we are given our mass, and we are given our velocity, and if you punch, so 13.9 is for v, 750 is for m. If you punch that into your calculator, the kinetic energy is 72,453.75 joules. And how much kinetic energy, what is the kinetic energy of the car if the speed is doubled? Instead of going back and doing all the math again, all you need to do is multiply by 4, because if you think about it, that's just simply 2v now. So it's just 4 times that. So just multiply what you just got by 4, and you get 289,815 joules. And how much work must be done to double the speed? Just simply this number, which you just got, minus the previous number, which we got, to get 217,361.25 joules. And a rifle can shoot a 4.2 gram bullet at a speed of 965 meters per second. Find the kinetic energy of the bullet. What work is done on the bullet if it starts from rest? Find the work done over a distance of 0.75 meters and determine the average force acting on the bullet. Now, first off, I've converted 4.2 grams into 0.0042 grams, and then I've converted 75 centimeters to 0.75 meters. And I typically like to cross that out because it's very easy to get misled and misread, so crossing out is something that I personally like to do. And kinetic energy, as we know, is 1/2 mv squared, all you need to do is punch those numbers into your calculator, and you'd get 1,955.5725 newtons. Sorry, not newtons, that's joules. Sorry, that was a mistake on my end. But yeah, that should be in joules. And what work is done if the bullet starts from rest? Obviously, it's still the same. And if the work is done over a distance of 0.75 meters, determine the average force. Obviously, since you know that work is made of force times distance, we can just simply divide the distance which we got to get 2,607.43 newtons. And the work done, keep in mind that work is just kinetic energy and potential energy. So yes, even though it starts from rest, you think it's not moving, you think you're not doing work, but in this case, we're talking about potential energy and kinetic energy, and so it's just basically the same answer from part 1. So that's in joules, not newtons, my bad. But the force is 2,607.43 newtons, and that is it for homework number 1. And homework number 2 says, a large chunk of ice with mass 15 kilograms falls from a roof 8 meters above the ground. Find the kinetic energy of the ice when it reaches the ground. What is the speed of the ice when it reaches the ground? Okay. So first off, we know that potential energy equals mgh and kinetic energy equals 1/2 mv squared. Now, when the ice is on the top of the roof, it has all the potential energy. There's no kinetic energy because that ice is ready to fall. It's ready to release that energy to fall. And then right when the ice reaches the ground, the kinetic energy is at its fullest and potential energy is at its lowest, because kinetic energy is the energy that is used for converting energy, or like, okay, well, basically kinetic energy is basically when the object is about to make contact with another object. That's kinetic energy at its highest, because that's when all the energy just simply goes to another object. And that's like when it's used, when it's moving, because as potential energy is at its highest at the top, it reaches down and potential energy slowly decreases, but in the meantime, kinetic energy increases. And from that information, we can conclude that the potential energy is the exact same when it's on its roof, about to fall, and right when just before when it's about to strike the ground. So from that information, since PE equals KE, all we need to do is first solve for PE, which we already know, because we have potential energy equals 15 kilograms times 9.8 meters per second squared times 8 meters. Punch all of those numbers into your calculator, and you get 1,176 joules. And since we mentioned earlier that potential energy is equal to kinetic energy, we can say that 1,176 joules equals half mv squared. So 1/2 times our mass times v squared. Punch those in, rearrange it, take the square root, and you get approximately 12.52198067 meters per second. And number 2 says, a bike rider approaches a hill with a speed of 8.5 meters per second. The total mass of the bike and the rider is 85 kilograms. Find the kinetic energy of the bike and rider. If the rider coasts up the hill, calculate the height at which the bike will come to a stop. assuming that there is no friction. How would your answer vary if the mass of the bike and the rider were doubled? Again, what I explained from number 1, we can make kinetic energy and potential energy equal to each other, because when the bicycle reaches the top and stops moving, that's when all kinetic energy is lost. Kinetic energy is basically just moving energy, and potential energy is like the energy that's ready to be released. And that's how I think about it. And so right when it stops, potential energy is at its 100% potential, it's full, okay? And kinetic energy is at 0. But as the bike rider approaches the hill, kinetic energy is at its fullest, and there's no potential energy. It's ready to use that energy. And so that means we can set them equal to each other. And the first thing we need to do is find the kinetic energy, which we can simply do by 1/2 mv squared. So it's 1/2 times our mass, 85, times our velocity squared, which is 8.5 squared. Plug those in, and you get 3070.625 joules. And I did mention that we can set the two equations equal to each other, and we get this. And resolving and rearranging, we can find that h equals v squared over 2g, because again, it is asking for our height. And plug that in, and we get about 3.68622449 meters. And since the masses cancel out when you set them equal to each other, in a frictionless environment, mass does not matter. Doesn't matter the mass, because it's negligible. Non-negligible, sorry. Mass simply doesn't matter because the m's cancel out. And number 3 is a 2-kilogram rocket is launched straight up into the air with a speed that allows it to reach a height of 100 meters, even though air resistance performs 800 joules of work on the rocket. Determine the launch speed of the rocket. How high would the rocket travel if air resistance is ignored? Now, there's a few ways to approach this problem, but the way I like to approach it is to ignore gravity. So imagine if it was just air resistance. How long would it last? And I drew a picture here. Hopefully you can see that. But basically, kinetic energy is at its full potential when it's at the bottom, right when it's about to start launching, 800 joules. The potential energy is 0 joules, right? Because that's when it's not like losing speed or anything. But when it hits the top, right when it hits the top, it's at 800 joules for potential energy and 0 joules for kinetic energy, because there's no more energy to go up. And so in other words, as potential energy increases, kinetic energy decreases as the height increases. And okay, we can find, this is our potential energy. 800 joules equals 2 kilograms, which is our mass, times our gravity, times our h. And we get about 40.816325 meters. And I call this the lost height because this is air resistance. And it says it can reach a height of 100 meters, including gravity and air resistance. But since I'm only including air resistance in this, that means that if we ignore air resistance, we add 40 meters for this number. And that means it's just 100 plus this number, which gets you about 140.81632653 meters, assuming the air resistance is ignored. And determine the launch speed of the rocket. And again, as we mentioned, we can set kinetic energy and potential energy equal to each other. So the usual, the m's cancel out. And how high would the rocket go? Just do a little bit of rearranging and punching those numbers in. You should get 52.53570.215 meters per second. And finally, on to homework number 3. And number 1 says, a 20-kilogram rock is on the edge of a 100-meter cliff. Calculate the potential energy of the rock. If the rock falls off the cliff, what is the kinetic energy just before striking the ground? What speed does the rock have as it strikes the ground? Okay. And okay, so first off, it's asking us for the potential energy. Obviously, we know it's mgh. So this is our mass times the gravity times our height, which is 100 meters, and we get 19,600 joules, which is our potential energy. If the rock falls off the cliff, what is its kinetic energy just before striking the ground? Again, at the highest and lowest points, kinetic energy and potential energy. Kinetic energy at its lowest point, right when it's about to strike another object, is at its highest, and potential energy right before the object is about to fall is at its highest. So this is actually both the kinetic energy and the potential energy. And what speed does the rock have as it strikes the ground? So Ke equals 1/2 mv squared. All we need to do is simply plug it in. Our 1/2 m is 10 because m is 20, so 20 times 1/2 is 10. So 1960 equals v squared. Raise that to the half power, and you get v to be about 44.27188.724 meters per second. And number 2 says a physics book is dropped 4.5 meters. What speed does the book have just before it hits the ground? Again, setting kinetic energy and potential energy equal to each other, canceling out terms, and rearranging it so that we have velocity equals the square root of 2gh. It becomes very easy from then on. All we need to do is plug in our numbers. 2 times 4.5, which is our height, times our g, which is 9.8, and we get about 9.39148550 meters per second. And that's our answer. Number 3 says, from what height would a compact car have to be dropped to have the same kinetic energy that it has when being driven at 100 kilometers per hour? The first step we need to do is convert 100 kilometers per hour into meters per second. And this is pretty easy and straightforward, but we know that an hour is 3,600 seconds, and 1,000 meters equals 1 kilometer. Cancel our units, calculate the numerator and denominator, and you get 27.7. I put a dash over the 7 because the 7 is repeating, meters per second. And from our problem from number 2, we know that v equals square root of 2dgh. And so you plug in our velocity, we plug in our we plug in our g, and do a little bit of rearranging to find that our height is about 39.36759889 meters. And I should have said this earlier, but if you actually check the answer key, the answers are going to be a little bit different because there's a lot of rounding that the answers do. And you can round if you want. Again, they don't have to be exact same as mine. I typically like to be a little bit more precise. So like if it's just like 1/100ths off, like don't do it again thinking you got it wrong, obviously. And anyways, number 4 says a 70 kilogram high jumper leaves the ground with a speed of 6 meters per second. How high can he jump? Again, set Ke equal to Pe. And rearranging to find out h, we get v squared over 2g equals h. And all we need to do is plug in. So our v is 6, our g is 9.8, and plugging that in, we get 1.836734694 meters. And that's our answer. And number 5 says, just before striking the ground, 900 kilograms smart bomb has 88.2 megajoules of kinetic energy. By the way, mega means a million, or 10 to the 6. If air resistance is ignored, determine the height from which the smart bomb was dropped. Determine the drop of the height if air resistance performs an 8.82 megajoules of work against the bomb as it falls toward its target. And again, from our previous problem, we can simply say that v squared over 2g equals h. V squared equals, and so what we're trying to find is the height, obviously. And so we have v squared times 1/2 times 900 equals 8.82 times 10 to the 6. Because, again, we are doing 1/2 mv squared. And so if you calculate for v, you don't actually have to calculate for v because you only need the v squared. So we solve that, plug v squared in, divide that by 19.6 because 2 times 9.8 is just 19.6. And our height is 10 kilometers without air resistance, or 10,000 meters without air resistance. Either one is fine, but yeah. And it asks for determine the drop height if air resistance performs 8.18 megajoules of work against the bomb as it falls towards its target. And in other words, it's pretty much just the same thing, except in this case, you add the two energies because you have to consider air resistance. And so it's literally the same process again. And so plug it in, punch it into your calculator, and you get 11 kilometers or 11,000 meters. This is with air resistance, and that's without air resistance. And finally, our last problem, number 6, says a 74-kilogram student starting from west slides down an 11.8 meter high water slide. On the way down, friction does 5,600 joules of work on him. How fast is he going at the bottom of the slide? First off, we need to calculate potential energy. All we need to do is plug it in, as usual, the mgh, and we get 8,557.36 joules. And now, without friction and air resistance, normally kinetic energy would equal potential energy, but since it says friction does 5,600 joules, you're not losing the energy. The energy is simply converted into heat. And so as a result, you're going to have to subtract 5,600 joules to get your potential energy right at the bottom. And you plug that into 1/2 mv squared, 74 times 1/2 times v squared. So that's 37 v squared equals 2,957.36 joules. Divide that by 37 and take the square root. And you should get v is approximately equal to 8.94028235 meters per second. And that is it. Hopefully this was helpful, and I hope you enjoyed it.